Before I start, I also want to thank all of you for coming and listening to this talk tonight. I also want to give a shout out to my wife who's here, and especially my parents who remind me that you're never too old to Shep Nachas. So thank you, Mom and Dad. Oh, and my father-in-law is also here. Hello from Brooklyn. Wonderful to see you all. Thank you. So yeah, I am super, super excited for this talk today. You know, usually statistics doesn't sort of evoke this passion in people, but I get so passionate when I think about, oh, my mother-in-law too, she's waving. I get so passionate when I think about Bayes' theorem. It's not just a theorem in statistics, it's a theorem, it's a guide for thinking about life and so many fascinating applications. I'm super excited to share this with you. It's my favorite theorem in all of mathematics, and I hope to share that passion and excitement with you in the next however long we're here for. So just by a quick show of hands, I can't see all of you. Raise your hand if you've heard of Bayes' theorem before. Anybody here? Okay, if you okay, we got some. Okay, very good, good stuff. Great. Well, what we're going to do today is talk about Bayes' theorem, and the caveat, not the caveat, but what I wrote in the description is you don't have to be a mathematician to enjoy, understand, or appreciate Bayes' theorem. There'll be a little bit in the middle, a little bit of mathematics that we'll explore. I don't want to be derelict to my duty as a mathematician to go into the rigor of it, but nothing too crazy, and I think we'll all be okay with that. So let's start. I'm going to start with the question, actually, and it's a two-part question. The first one is relatively tame. It goes like this. I have two children. The eldest is a girl. Find the probability the second is a girl. This is not meant to be crazy tricky. Feel free to call it the answer if you think you know it.
1 in 2, 50%.
1 in 2, I heard. Okay, very good, Leonard. Thank you. And yeah, if you agree with Mr. Shakin, correct. The eldest one is a girl. This doesn't affect the next child being a girl or boy, presumably. We could say 1 in 2. For the next question, though, instead of doing calling, I'm going to ask people to please use the chat. I'd like you please to share your answer publicly to this question. And if you're feeling brave enough anyway, but don't be too stressed about it. It's a question that's harder than it might seem at first. I have two children. At least one is a girl. Find the probability that they are both girls. Okay.
Is that a word?
Again, I have two children. At least one is a girl. Find the probability they are both girls. We're not feeling very brave yet, are we?
Yeah.
Maybe a third.
Oh, I heard a third. Okay. You could also call it out if you don't want to chat it. Put it in the chat box. That's fine too.
I just want to, can I just
1
mention,
in 4.
Kraus, what's fascinating about this? I can't believe, I think I'm a bright guy. I feel like my brain is exploding thinking about this simple, this like seems like the most simple question you could possibly ask me, and I feel like I need to take a nap.
Inbox.
Except that it's not so simple, Rabbi Kroll. It's actually pretty deceivingly difficult. So don't feel bad. And my goal is not to make you all here feel, I don't want you all thinking that this is going to belittle your mathematical sense. We're going to explore this. Okay. So, if we're not feeling up to it, that's fine. We're feeling a little bit shy, or maybe afraid to expose our ignorance. It's all good.
Mickey said 1 out of 3.
What?
Mickey said 1 out of 3.
1 out of 3. Is that your? Is that my Mickey? Oh, okay. Yeah, Mickey's a sharp kid. That's it's good to bet on Mickey. Well, let's see. In this talk, we're going to discuss the following. We're going to come back to this question very soon. So, I'm going to keep it in suspense for about 5 minutes. We're going to do an introduction to Bayes' theorem. We're going to talk about how Bayes' theorem works. We're going to talk about applications of Bayes' theorem, including finding the USS Central America and its gold treasure, the largest treasure ever found in the history of America. We're going to talk about determining who wrote the Federalist Papers using Bayes' theorem, and false positives of medical tests like COVID-19, and a more general application to everyday life. All right, a little bit of history of Bayes' theorem. This is Reverend Thomas Bayes himself. Thomas Bayes lived from 1701 to 1761, and he's credited with the discovery. His work actually came to light after he died, and it was named after him. It's actually interesting that probability is one of the more recent newcomers to the areas of mathematics. We think of geometry as being the realm of the Greeks, and some of the other, trigonometry also came much earlier. Probability was really only about 300 years old. It was discovered by Blaise Pascal. You might know from Pascal's wager if you teach or know Jewish philosophy. And also Pierre de Fermat, his name might sound familiar because of Fermat's last theorem that was famously solved in 1991, 300 years after he came up with that. But anyway, Bayes' theorem is only about 300 years old, and his formula became increasingly prominent in subsequent centuries and forms a background of statistical reasoning today. What is Bayes' theorem? Okay, don't get too scared here. It's as mathematical formula go, doesn't have integral symbols and calculus. It's just relatively simple. It says this: the probability of A given B, this little line here is given, is the probability of B given A times the probability of A over the probability of B. We're not going to go into the numbers just yet. I don't want to, scare you all get running for the bedroom if I go into this too much right now. But what this is basically saying is as follows: you start with an initial belief, you add the recent objective data that's come your way, and you come up with a new and improved belief. I'm going to share this with you with a very simple example. Before I do that though, this formula is used to sort spam from emails. Google's using it, assess homeland security risks, decoding DNA, and I mentioned the Treasury we're going to discuss, the Federalist Papers, false positives. It's also really at the heart of modern statistical inference and a way to think about one's own beliefs. We're going to explore a lot of this over the next bit of time we have together here. Let's start with a simple example. I promise this one is fairly straightforward. I selected the day of the week at random. What's the probability that it is Monday? All right, feel free to call this one out. I don't think you're going to get it wrong. What's the probability that it is Monday? Go ahead.
1 in 7.
1 in 7. All right, very good. Nothing too crazy there. 1 in 7. Okay, part 2. What is the probability it is Monday given that it is not the weekend? Given that it is not the weekend. All right, feel free to call this one out as well.
1 in 5.
1 in 5. Okay, do we agree with Mr. Shakin?
Why am I not getting credit here?
I don't know.
Yes.
I think it's Jonathan who's speaking. I'm not.
I said that. 1 out of 5. Yeah, we've got 1 out of 5 here at the Harris house.
Wait, did Mr. Kraus freeze?
Yes.
I thought he was staring into my soul, waiting for me to come up with an answer. I'll tell you one thing: if Mr. Kraus's internet doesn't come back soon, you're going to be in. I hope you're not looking to. Well, we'll look to Ms. Schlaff. You went to college with Mr. Kraus, Ms. Schlaff?
Mr. Kraus and I went to college together.
Yes, so I
Indeed.
assume that if he knows all about Bayes' theorem.
I did take statistics in college, 2 semesters.
Okay, so in that case, I assume.
I'm continuing with Bayes' theorem here, and that was the last math course I ever took.
What happened?
This is just his way of getting us so hyped up to understand Bayes' theorem. Please don't leave. I assume.
We have a storm here in White Plains right now, which may have cut his signal.
Oh, it's possible. Storm. Yeah, I'm feeling the storm also as
Go
well.
away for a minute and look what
Hold on.
happens.
Mr. Kraus made a very good shullent in college. I can tell you that.
I'm going to call him on
That I remember.
see if his internet is in fact down. And if it is, I'll be very sad. But hold on a sec. Maybe he'll call. He can call him from his phone, I suppose. Hold on.
Yeah, he could do that.
Okay, Ms. Schlaff, entertain the crowd while I find
I just heard thunder in Riverdale.
I just spoke with Mr. Kraus. He's on the way back in. He has
on the way back.
some
Great.
internet trouble.
Great. Because otherwise I was going to sing, and that would not have been fun for anyone.
As we wait for Mr. Kraus to get back in, I mean, of course it's 1 in. I don't understand how is it not. Why is he making us feel Can someone explain to me why it wouldn't be 1 in 5? If
I
you
think
take
'cause
out,
there's still 7 days in the week. So you
you
might,
took out Saturday and Sunday.
well, I don't know. I'm not sure about that, that's what you do. So I'm a little bit
I thought it was given that it's not Saturday or Sunday.
It has to be 1 in 5.
I think he's just setting us up for a harder
Okay.
question. So
Yes.
he's lulling us in with easy ones.
That.
This is the problem. Whenever he asks these questions, I feel like my instinct is that I think is the right answer, I don't say because I say the wrong answer.
All right, here comes Mr. Krauss, everybody.
It's the suspense. Now we're all in suspense.
Can you hear me?
Yes. Welcome.
All right, we're back.
Hooray.
We don't hear you.
Computer audio.
Now you
Okay, how's this?
Alon, everybody figured out the answer while you were gone.
Well, good. I purposely gave you that time to stew over this a little bit, you know, and think about that. Was it beneficial?
No.
We'll find out in a minute.
Okay. Rabbi Bloom, though, I cannot share my screen. So can you give me that access again?
Yeah, here we go. Rabbi Kroll, co-host.
There you go.
All right, Mr. Krauss, go for it.
Excellent. Okay. And we are back. Okay. Let me just get this on present mode. Okay. Well, let's go back to our original problem. The probability of both girls, given that at least one's a girl. This is confusing for people. And here's the correct answer. Once I state that I have at least one girl, there's one option I eliminate. Let's go through the 4 options at first. I can have a boy first, followed by another boy. That happens 1 out of 4 times. I can have a boy first, followed by a girl next. That happens 1 out of 4 times. I can have a girl first, then a boy, 1/4 of the time, or a girl and then a girl. That happens 1/4 of the time. Once I state the given that I have at least one girl, I no longer have this as a possibility. Instead, I have 3 equally likely outcomes, of which of those 3, one of them is the girl and the girl. The probability of 2 girls, given that I have at least one girl, is surprisingly for most people 1 out of 3. And this is extremely counterintuitive. And you know, when I teach this to my honors 10th graders, they often get this wrong. They think, well, it's probably still a half, or maybe it's a 4th, or whatever it is. But it's actually 1/3. This is all really an introduction to Bayes' theorem. Just getting our appetites a little bit wet, because we're gonna explore some really amazing things. We're getting into philosophy and life and all sorts of good stuff. Let's explore this idea of given a little bit. This actually came up in the O.J. Simpson case. Here we go. In the murder trial of O.J. Simpson, his lawyer, Alan Dershowitz, said, an infinitesimal percentage, certainly fewer than 1 in 2,500 of men who slap or beat their domestic partners go on to murder them. Thus, he implied that the chances that O.J. Simpson was the murderer was quite slim. So I'd like to open it up now and ask you, why is this a spurious argument?
Because there was a dead body before them.
Okay, good. I couldn't see who that was. Mr.
Sorry, it's me, Andrew.
Oh, Andrew Small. Okay, good. Good. There's a dead body. Good. Right.
And there's other evidence.
And there's other evidence. Okay, good. That's all certainly true as well. Let's explore this using the notation we saw before. His claim was that the probability that a husband will murder his wife, given that he abused her, is very, very small. If you kind of sit with this a little bit, you realize that's absolutely irrelevant, because what we have here is a dead body. The real question is not what's the probability someone will murder their spouse if they abuse them. What's relevant is what's the probability that the murderer is the abusive husband, given that there was a woman who was murdered. And you know, if you're not really thinking critically about this, you might fall for that and say, yeah, you probably didn't do it. Chances are so small. No, the chances are probably pretty high. Okay, let's go further with this now. This is my favorite problem, probably in all of mathematics, my favorite theorem. I just love this problem. I think it's fascinating. And with this problem, I'm going to get a little bit into the meat of the mathematics of Bayes' theorem. And you know, if that gives you nightmares, I apologize. I promise it'll be over soon. If you're kind of excited for that, that's great, because I get excited for this too. Here we go. You have 6 coins of the same denomination in a bag. 5 of them are standard coins, but the 6th is double-headed. You take one out at random. First part's a little bit of a gimme. What's the probability you have the double-headed coin? Okay, call it out.
1 out of 6.
1 out of 6. Thank you. This one's not tricky. 1 out of 6. 6 coins in a bag. 1 of them is double-headed. Now here's the amazing problem. You take 1 coin out at random from the bag and toss it 4 times, and it comes up heads all 4 times. What's the probability that you have the double-headed coin? I find this fascinating, and here's why. First of all, before we do that, actually, I'd love to have some guesses. I'm not expecting you to do the math here, even if you remember Bayes' theorem. You know, I'd love to see some chats, maybe just taking a random guess. What do you think it is? You know, 5%, 95%.
1 coin at random from bag. And
any number.
Comes up heads every time. What's
probably
the
like 3 and 4. Pretty small.
Yeah, let's write it down in the chat. Can we do the chat?
Sure.
Yeah, oh, are we not familiar with the chat room?
I got the formula. I could do it.
Okay.
Probability. Okay.
Feel free to be brave. Guess the number.
16.
Right, pretty small. Now, right?
Okay, we got it. Okay,
94%.
Still 1 out of 6, very small. 6. I have some students here. It's not fair, Ben. Okay.
5 over 6.
30%, 1 and 6. First of all, thank you for being brave. I appreciate that. That's great that you're trying some.
Half to the 4th. I don't know if that's right.
What do you think that is?
The chance. The chance.
1 and 16. Ooh, wait, is that a binomial theorem there, Jonathan Hecht? It's good. Good stuff. Okay.
Certainly is.
Shall we explore this then? Here we go. What I find, before I give the answer, what I find amazing about this is as follows. There are 2 equally incorrect ways of looking at this that take in only the extremes. One incorrect way of looking at this is to say as follows. It's got to be the double-headed coin. Because, look, you got 4 heads in a row. You know, it's got to be the double-headed coin. I mean, how often does this happen with a regular coin? Incorrect. Equally incorrect. You know, Alon, the chances you got the double-headed coin in the first place was only 1 out of 6. This has got to be coincidence. You know, certainly you got the regular coin. Equally incorrect. Those 2 extremes are wrong. The answer actually lies. We can get a precise answer out of this with this formula. Let's do it. Okay. So here's the problem. Again, I wrote it out again. The best way to understand Bayes' theorem is through a tree diagram. You have 6 coins. The probability you choose the fair coin is 5 out of 6. If you choose the fair coin, the probability you get 4 heads, that is heads, 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 is 1/2 times 1/2 times 1/2 times 1/2, or 1 out of 16. Anything else is just 15 out of 16. If you get the double-headed coin, well, you're guaranteed to get 4 heads. It's just 1 over 1. Now, since I stated that you flipped 4 heads in a row, there are only 2 scenarios that are now relevant. This guy and this guy. The other 2 do not concern us because that's not what happened. Only these 2 are relevant. How does the math shake out? Next slide. Applying the formula, we're actually going to get a little bit rigorous here. And if this is over your heads, don't worry about it. We're going to get right back to like more conceptual. But I want to be a little bit rigorous with this slide here. The probability of A given B equals the probability of B given A times the probability of A over the probability of B. Let's break this down. the probability you get the double-headed coin, given that you flip 4 heads. I've identified the double-headed coin as A. A is having the double-headed coin. B is getting 4 heads. Our denominator, the probability of B, that is the probability of flipping 4 heads, amounts to all the ways we could have gotten 4 heads. And as I said before, there are 2 ways it can happen. With the fair coin, right here, whose probability is 5/6 times 1/16, or 5/96. Or I could have gotten 4 heads by choosing the double-headed coin, 1/6 times 1, or 1/6 in total. These 2 combined are the 2 ways that I could get the given, my denominator, which amounts to 21/96. Our numerator is the question we were asking. What's the likelihood it is in fact the double-headed coin? We established that as 1/6. If you want to be rigorous, it's the probability of A, which is getting the double-headed coin right here. And then the probability B given it, the probability you get 4 heads given that you got the double-headed coin, which is guaranteed because you can only flip 4 heads if you have a double-headed coin. So our numerator ends up being just this value over here, which is 1/6. When we do 1/6 over 21/96, we get a precise answer of 76.2, or as Ben Wexelblad, nice job, but you're paying attention. And during Zoom learning, he got, that's great stuff, Ben, is 16/21, an exact answer. I love the fact that you can get a precise answer out of this. It's just beautiful to me. It's beautiful to me for a lot of reasons we're going to get into. Now, if this doesn't quite work for you, if you're a little bit confused by this, I'm going to share one other way to understand this. And then it's as follows. This one's a little easier. Instead of doing probability, we'll actually do numbers. Suppose I did this simulation 96 times. I chose 96 because it works as a common denominator. How often would I get the double-headed coin? Well, 1/6 of the coins are double-headed, so I would get that 16 times. And I would always flip 4 heads. How often would I get the fair coin? 5 out of 6 of those times, or 80 times. Out of those 80 times, 1 out of 16 times, heads, 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 1/2 to the 4th power, 5 times, in other words, that's 1/16 of 80, I would get heads 4 times in a row. Since I gave the given as I have flipped 4 heads, the only 2 numbers that concern me here are these 16 and these 5, and that forms my denominator. Out of those 21 times, how often was it in fact the double-headed coin? 16. Hence my answer is 16/21. We're going to try to understand this a few other ways if this doesn't quite sit well with you, or if you're confused. We're going to see it visually in a minute through a video, and then we'll see all sorts of amazing applications of this. But for now, let's go on. Through an understanding of Bayes' theorem, we can, this is what I think is so profound about this, we can really eschew extremes and come to a precise probability based on given information. Robert Rubin, the former Secretary of the Treasury under Clinton, wrote in his book, In an Uncertain World, he said, in a world without provable truths, the only way to refine the probabilities that remains is through greater knowledge and understanding. And that's exactly what we've done. You start off with 1 out of 6, but you have new information now. The new information is you flip 4 heads. So that refines our probability and understanding as to what we actually got when we pulled out the coin in the first place. Okay, now a little more, we'll go back to an interactive question here. Tom is a university student. He is shy, he doesn't make eye contact, and he mumbles a lot. Would you say he is more likely to be in the PhD program in mathematics or in the business school? So I can't see all of your faces here, but for those whose faces I can see, we'll do like this. If you think the answer is the math PhD program, please hold up 1 finger. If you think the answer is the business school, please hold up 2 fingers. Okay. All right, I'm seeing a few, 1s and some 2s. Would you mind, I'm going to put you on the spot a little bit, either one of the hechs. Would you mind sharing why you thought 2?
Probably because the PhD program is part of the business school, or in general, there's just so many more people in the business school than in the PhD program.
Interesting, interesting. So maybe we sort of think that math PhDs tend to be more introverted, but maybe there's just so many more business school students that makes up for the fact. So let's frame this in Bayesian terms. What's the probability Tom is a math PhD student given that he is very introverted versus what's the probability Tom is a business school student given that he is very, very introverted? There's one problem with this question and why it can't be answered yet is because we don't know the priors. In other words, if I said to you, what's the probability of getting a double-headed coin given that you flip 4 heads in a row, you would need to know in the first place what fraction of the coins in the first place are authentic versus double-headed. Similarly here, what fraction of students are in the business school versus the math PhD program? Let's watch a video. This is a wonderful video. There's a woman named Julia Gallup, who's the founder of the Center for Applied Rationality, who does all sorts of wonderful talks. She even did a TED Talk on this, and I'll let her explain it. She does a wonderful job. As soon as I can get this open. Okay. Computer's a little bit slow. This is where, there you go. This is where Bloom tells me to get on my Mac instead of my PC, but old habits die hard.
I didn't say a thing.
Okay.
I will later. You want to send me the file, Alon, and I'll play it?
Okay, here we go.
Oh, there you go.
There's another piece of information that's relevant and that people tend to forget when answering this question, and that is, how many math PhDs are there relative to business school students? There's a lot fewer. The numbers will vary from school to school, but it's something on the order of 10 times as many business school students as math PhD students. So we have these two pieces of information about there being many more business students than math students, and also about shyness being more common among math students than business students. And the question is, how do we combine these two pieces to get one overall estimate about Tom? This is where Bayes' rule comes in. So you can imagine that this divided rectangle represents the relative proportions of math to business students, very roughly speaking. We'll put it at 1 to 10. And now looking just at math students, we can ask, how common is shyness? I would very roughly guess that it's about 75% of math PhD students come off as shy. And now looking just at business school students, again, guessing roughly, I'd say about 15% of business school students come off as shy. So now we've represented both of those pieces of information in one diagram, and we want to know whether Tom is more likely to be in a math program or a business program. We don't know which one he's in, but we do know that he's shy, which means that he must be in one of those lavender rectangles, right? Because those represent the shy math and the shy business students. So to get a sense of the relative probabilities of him being in math versus business, we just have to compare the relative sizes of those lavender rectangles. And it looks roughly like the lavender business rectangle is about twice as big as the lavender math rectangle. And you can see how the math shakes out. We just multiplied two linear ratios, the ratio of math to business students, which we put at 1 to 10, times the ratio of shyness in math versus shyness in business, which we put at 75 to 15. And multiplying those two linear ratios gives us a ratio of areas, which comes out to about 1 to 2. So roughly twice as likely for Tom to be in the business program, even though shyness is more common among math students.
Okay.
So this is the mechanics of Bayes' rule.
Okay, great. So, you know, what's important is the prior. The prior is that there are many more business students than math students in the first place. Okay, I'm going to keep it actually off presentation mode so it'll be easier for me to go to the next video. This next example is fascinating. They actually found a sunken treasure using Bayes' theorem. A little bit of background. In 1857, the SS Central America sank off the coast of North Carolina, carrying 15 tons of gold valued at over $500 million. In 1988, Tommy Thompson and his team used Bayesian search theory to find the treasure. How did that work? So before I show the video, I'm actually going to just go to the next slide and share with you how this sort of plays out. Okay, recall, Bayes' theorem starts with an initial belief, brings into the picture recent objective data, and then you have a new and improved belief. It is a continual process with newer sources of information continually updating what we believe is true. As an example, recall the double-headed coin problem. After 4 heads, we computed the likelihood you have the double-headed coin, and we said it's now 76.2%. Now, if another person flipped the same coin 2 more times and got 2 more heads, we would reapply Bayes' rules. But our probability is no longer starting at 5/6 and 1/6. I instead write this, oh no, we have information. This is now 0.762, and this is 0.238. So with this iterative process, we continually refine the probabilities of our priors based on new information that come in. And that's exactly what they did to find the SS Central America. Let's see. We're gonna watch about 5 minutes of this video. It's from a ABC and ESPN also contributed to this short little documentary, wonderful one. Here we go.
In this particular instance, there is no X marks the spot. And that's where the search theory mathematics comes in.
What Bayesian search theory is about is taking a whole mess of different kinds of data and putting them into a common framework that we can actually then use to search.
So it's a way of taking many strands of information and weaving them into a central theory.
Each of those pieces of information on its own might be very weak, but when you put them all together, you get more powerful information than any one of them individually. And you apply a mathematical formula called Bayes' rule. That very simple equation is the foundation of today's information theory. If you go on the internet and type something into a search engine, that search engine is going to use Bayesian theory in calculating the results.
Bayesian modeling could take large sets of data, sometimes with conflicting information in it, to create a collective whole understanding of where the truth probably lay. That's why we collected every piece of data that we possibly could.
In 1984, I received a letter from Tom Thompson, just out of the blue, asking me if I would be interested in helping him out with to plan a search, and he wasn't very specific about what the nature of the search was.
Larry Stone had been involved in the search theory that found the hydrogen bombs that we lost off of Spain. His work had been used in the finding of the sunken submarine Scorpion. This guy wrote the book on how to find things lost at sea, and that's about all I needed to know.
I first signed a non-disclosure agreement because he was very secretive about this. He was worried about other people going out and finding the ship before he had a chance to do it. This is in some way outlandish. I mean, here you're going to go hunting for this ship that had all these gold coins and bars that sank 30 years ago. To me, that just was an amazing prospect.
And Bob asked a lot of questions. Tommy asked him a lot of questions. Stone was drawing stuff on the blackboard, explaining, here's the velocity of the wind, and here are the waves coming in, and it would be X, this would be over here so many hours later. Bob looked at Tommy, and Tommy nodded, and Bob opened the suitcase, and it just sprang open, and it was this gigantic 12 by 12 data correlation matrix. And we laid this package of data in front of them and say, this is what we're working on. Do you think this is something that you can use? Can you use anecdotal information that's tightly pulled together like this and create algorithms to find something that was lost at sea? I put together a combined narrative where I gleaned out what I felt were important pieces to serve as a thread to kind of give him a handle on this massive amount of data.
Even if you think the information is not of as high quality, you still do not throw it out. You put it into the probability map, you just give it a lower weight.
So Larry Stone actually sat down and tried to build a Bayesian model of all of the factors that could go into figuring out where this ship was.
Bob would not be able to do the sort of a Bayesian analysis that I did, so together we made a complete team in that sense. He's the data on the processor. I organized the information in the correlation matrix into 3 scenarios. These scenarios give you enough information to estimate a position of some sort. The probability map covered an area about the size of Rhode Island.
What Larry was able to do was to use this Bayesian search theory to come up with an optimal path for searching for this ship.
And the equipment that we were planning to use was a side scan sonar that was capable of a...
Okay, I'm going to pause it and just show you now. Let's see if I can back up a little bit. Maybe not. But that little map they had there.
5,000 meter swath. That was our lawn mower going up and back and up.
Okay, I can't seem to rewind from this. Okay. Okay. But that map basically was used Bayesian analysis. What they did was every single pixel, so to speak, every little I don't know how large it was, of ocean, you say, what's the probability the treasure's there? Okay, we start with whatever, 1%. You feed in new data. Oh, based on that report about the wind from this sailor in that publication, now it's less than 1%. Oh, but we have another account from this person, we weighed more heavily, now it's 2%. And they came up with that map, and they actually did find it on that map they created. It was one of the lower probability areas, but they did find it, which is just an amazing finish to the story. Actually, the real finish is not that amazing. He ended up absconding with the money and not paying off his investors, but that's maybe for another time. Anyway, so let's go back to where we were. I'm going to do a few more examples. One more example involves a little bit of history, which is the Federalist Papers. And again, I'll keep us just not in presentation mode, because we're going to watch another very short video on this. And then we'll talk about COVID-19 and how this relates to false positives. And then we'll go into a little bit of sort of life philosophy and wisdom. So the Federalist Papers was written in these 2 years, apparently, by Hamilton, Madison, and John Jay. The author of 12 of those essays was unknown, and they knew it was between Madison and Hamilton, but their writing style was kind of similar. They weren't sure exactly who it was. 175 years later, statisticians Mosteller and David Wallace used Bayes' theorem to determine the author. I find this also to be an amazing example. One more short video for you on how they use Bayes' theorem to determine who wrote the Federalist Papers. Anybody here know? Call it out. Do you know who actually they found was the author of those 12 essays? No, not sure. Okay.
Thomas Paine.
Hamilton, right?
It actually ended up being Hamilton. Yep, very good. It was Hamilton. But let's see. Short clip.
Two statisticians decided to take a crack at it. They took articles in which they knew whether Hamilton or Madison was the author and analyzed certain words that one used more than the other. Their writing styles were extremely similar, but words like while, whilst, upon, and so on were a few words of interest, since, for example, Madison rarely used the word upon, whereas Hamilton did. In fact, throughout 49 of Hamilton's papers, they found that the word upon came up 3.24 times per 1,000 words on average. After analyzing all the known papers of both Madison and Hamilton, a comparison could be made showing a big difference. When faced with a mystery article, the statisticians first assumed 50-50 odds that it was written by either author. They would then analyze the frequency of 30 words of interest and update the probability using Bayesian statistics. New given information like how often a word would appear allowed for a more updated and accurate probability of who wrote it. Now, they first ran this test on known papers of Hamilton and Madison, and it predicted the author correctly every single time, and not just by a little. The most inconclusive result occurred when running the numbers on an article written by Hamilton, and it still said there was a 95% chance that he was the author. So the test seemed accurate, and when it finally came time to test the 12 mystery articles, the result said every single one was written by Madison.
Okay. By the way, for those who are familiar with computers, this is also how the process of neural networks basically works. Like handwriting analysis, when you do those, let's say you're writing handwriting, and a software has to analyze what it actually is, and so it can convert it to type. They're using Bayesian's rule as well. Okay, now I want to get into the last example, which is false positives. Before I do that, maybe maybe have some questions. I see some chats. Let me pause for a second. Okay, James, that's a great question. Could it still been written by Madison? Yeah. He actually, I like what the author of the video says. He says, it doesn't show for sure that it's a Madison, but it just gives very, very strong evidence in favor that it was in fact Hamilton. So yeah, okay, it's pretty funny. Okay, so any questions now before I go on to false positives? Okay, all right, cool. So let's go on then. Okay, false positives in medical cases. Fascinating problem, and if you went to medical school, then this kind of example might sound familiar, although it might have been a long time ago. Here we go. Imagine you go to the doctor for a routine checkup, and the blood work comes back, and you test positive for a fairly rare form of cancer that affects only 1% of Americans. The doctor reports the test is 90% accurate. What is the actual likelihood that you have the disease? So I'm curious, I'd love to see what you think might be the answer. Maybe we can do some more chats here. If you think you have an idea, you can still, I'm not testing on the math here, just any thoughts what you think it might be. What's the actual likelihood of your illness? Feel free to chime in if you're feeling brave.
It's a false positive.
Yeah, this is actually, I'm asking you what's the false positive likelihood. I'm asking you what's the actual likelihood that they got it right. Okay, so Mickey's got about 1 in 10, a bit less than 50%. Good, thank you, folks. It seems like it should be 90%. It seems like the most logical answer you can give is that, well, yeah, the test is 90% accurate. Accurate being defined as that you actually have it.
So 1% chance.
So 10% false. I need the sensitivity, specificity, not the accuracy.
Okay, let's explore together. Here we go. We're going to use this tree diagram again. First, I'm going to frame it as conditional probability. What's the probability you have the disease given that you tested positive? The answer might surprise you. Well, some of you. Let's imagine, we'll do it with numbers instead of probabilities. It's a little easier to follow. Imagine you have 10,000 patients. H stands for healthy, S stands for sick. Since the disease only affects 1% of people, only 100 people are going to have it. 9,900 are going to be healthy. Okay. Of those that are healthy, the test gets it right 90% of the time, which means 8,910 times you'll get the true negatives, which is correctly saying you don't have the disease. But the test will get it wrong sometimes. 10% of that 9,900, which is 990 people, will be false positives. It'll say they have it, but they actually don't. The flip side is that 100 people actually have a disease, 90% of the time they will correctly be identified as having it, which makes 90 true positives. You can start to see what's going on here. Next slide. Okay, there are a total of 1,080 total positives. Of those, 990 are false, which means it's a 91.7% chance you do not have the disease, or less than 9% chance you do have the disease. And the intuition behind this goes as follows. Yes, the test is 90% accurate. It's usually going to get it right. But there's only one thing that's even more unlikely to happen. And that is that you actually have the disease in the first place. Make sense? Okay, I'll take that for yes. So by the way, there's one caveat, very important. If the general prevalence of an illness is 1%, but you have symptoms, your likelihood is clearly much greater. So, if the doctor says, did a blood test on you and turns out you have malaria, and you say, oh no, I read this only affects 1% of people, and the doctor says, well, weren't you just in the Brazilian rainforest and you have fever? And oh yeah, well, your probability is not 1%, your probability is obviously much higher. But it comes to play when you're doing, for example, random tests in COVID-19. Let's explore that next. New York Times had an article, or actually its opinion, just because you test positive for antibodies doesn't mean you have them. In a population whose infection rate is 5%, a test that is 90% accurate could deliver a false positive nearly 70% of the time. You may wonder, how is this possible? Where are they getting this from? Well, we know where it comes from now. Here we go. The antibodies are said to be present in 5% of people. Actually, the New York Times is a little bit, conservative with that. I've read 5 to 15%, but we'll go with what they said for now. No antibodies in 95% of people. The test is 90% accurate, which means 90% of the time, if you have it, you'll test positive. Negative, 1%. Okay. If you don't have the antibodies, you'll get a false read 10% of the time. Now, the only things I care about here are the times when you test positive. This time and this time. This together forms my denominator. 5% times 90%, that's here, or 95% times 1%, these two. Those form my denominator because that's what I'm interested in. I'm only interested in cases where you tested positive. And of those, how many, what's the probability you actually, you get a false, I think I did a false read here. A false read, this is the false read, where you have it and, where you have it and you, oh no, this is an actual true read. You have it and you test positive, which is 32%. So if we go back to the article, so the article said you get a false positive nearly 70% of the time. Actually, it's about 68% of the time, because 32% of the time, you actually don't have it. Or you get a, I'm sorry, it gets it right only 32% of the time, and it gets it wrong 70% of the time. That's not a very good test, not a very accurate test. And obviously this will change a little bit if you're only getting tested if you have symptoms, et cetera, et cetera. But just randomly testing people will yield a lot of false positives and just get it wrong most of the time. So I'm going to sort of go into a little bit of, I guess, if you will, a little bit of life wisdom, I think, because this really speaks to me, not just in terms of false positives and finding treasures. I think that stuff is really interesting. But for me, it's really a much deeper theorem than that. And I want to just address that. But before I go on to the last slide, I guess any other questions, you can just call it out because I think I lost a visual on you. Question came in, what if you test positive for COVID before you take the antibody test? I think that'll be different because it says if you're tested positive, then your probability you have the antibodies is not 5% anymore. You'd be somebody who probably have a reason why you took the test, and the test is, that lends itself to a higher likelihood that you actually have it. So again, we have to judge, this isn't a case where you really just were being randomly tested, having no reason to test yourself, you per se, based on symptoms. Okay, let's go to Bayes' theorem in life. I think there are a few take-homes for me. One is, can we be comfortable with beliefs that are grayscale? And I think this is a kind of a tricky thing. We like to think of our beliefs as being very firm. Oh, I believe in this, I believe in that. It's absolutely has to be this, has to be that. And I think what Bayes' theorem teaches us is that our beliefs can really, maybe to be comfortable with a belief that is on a grayscale, a percentage, and not think of things in absolutes. And furthermore, what's really crucial, I think, is when new information enters the picture, do we rationalize our entrenched positions, or are we open to changing our beliefs? And one example of that is, let's just say, you have an impression of yourself as a good driver, and you think, oh, I'm a good driver, and then one day you hit a tree. So they just came out of nowhere, right? So you could say, you could rationalize your what occurred with you being a good driver by making sort of certain rationalizations. Yeah, that I was tired that day. It's very unusual. It was bad weather. I was distracted by someone else in the car, but really I'm still a good driver. But really, I think what Bayes' theorem comes to teach us is that every new bit of information that occurs to us should perhaps sway our way of thinking a little bit. It doesn't mean we're now guaranteed to be a terrible driver. It means that we have a little bit of evidence now to suggest, well, maybe we're not as good a driver as we thought, and we have some evidence now that we're not. Or another example is maybe a little bit out there, but let's say we're talking about aliens, and we think there's maybe we have a preconceived idea that there's a 10% chance that there are aliens and that are visiting our planet, and then your best friend, who you've always known to be a person of integrity and you can trust, comes and says, you won't believe us, last night I got abducted by aliens. It was crazy. This just happened to me, and I can't explain it. I can't even prove it. It wasn't a dream. This really happened. Now, there are two extreme ways to think about it. One is this person's crazy. I'll leave my probability 10%. Or you could say, wow, that's really amazing. It must be now. It's absolutely true. I think a more nuanced way to think about it is, well, there's a little more evidence now in favor that there might be aliens. Maybe it's not compelling enough for me, but it lends itself to that a little bit more. And another way to sort of think about it is, do we see what we believe or believe what we see? If we see what we believe, then we're open to, let me do the other way around. If we believe what we see, then we're kind of approaching this with an open mind and saying, oh, I see this, let me adjust what I believe to be true. But the ego mind sort of oftentimes wants us to only see what we believe, and whatever we see, we just sort of make it a part of our preconceived ideas. And I'll leave you with a quote from I can't even read who it is. I don't know. Probably someone famous, because it was on the web. To have a strong opinion all the time is corrosive to a person's intellect. It becomes your default position. Or as I once read in a book, it's good to have opinions, but positions not so much. And with that, I want to thank you for engaging me in this conversation and really giving me the opportunity to share my favorite theorem in mathematics, something I'm very passionate about, something that's really impacted the way I think about life and decision making in many different ways. So thank you so much again for coming, and I wish you a wonderful night.
Thank you so much, Mr. Krausz. That was incredible. Again, what a treat it is for us to sit in your classroom, even virtually, to gain a glimpse of your passion and the clarity by which you can really break down really complex topics, even for those of us who are not as mathematically inclined as you are. So thank you very much. That was really a tour de force. Thank you, everybody, for joining us, and thank you, Mr. Krausz.
Thank you so much. Thank you.
Mazel tov.
And if you do want to stay behind, feel free. I'm not going anywhere just yet. You can feel free to ask questions. Thanks.
Alon?
Yeah.
I was thinking of how this relates to the Monty Hall problem.
Yeah, it's a great question. It's a great question. It actually does not. And the reason why it does not is because in the Monty Hall problem, it's a different situation, because the host, Monty Hall, actually knows where the car is. So when he says it's not in this door, he's actually giving away a lot of information. So in that case, when he opens up a door, let's say, for example, you choose one and he shows you that door 2 is a goat. So you now have a choice to stay or switch. The mathematical probability is 2/3 you're likely to get the car if you switch, 1/3 if you're not, because he only opens up the gate, the door, the curtain that does not have it. He will never open up the curtain that does have it.
Okay.
I'm not doing a whole lot of justice al regla achat here in one bit, but that's the answer. It's actually related, but a different kind of question. But that's a great question. Oh, I have to give a shout out to my brother, who's also joined. Daniel Kraus, thank you so much, with my niece and nephew there. Beautiful. Thank you. Any other questions? I'll stick around.
Yeah, I have a one question.
Sure.
Yeah. So does it matter where you start in terms of how much information you have?
Yeah, I think if I understand your question correctly, you have to have some prior, meaning some prior ideas about what is truth. Whether it's with aliens, my prior is 10%. Whether it's with the illness, the prior is 1% because there's a 1% chance you have the illness. With COVID-19, maybe it's 5%. And with the treasure hunting, they kind of gave a somewhat arbitrary initial probability. Oh, the likeliness in this pixel of water is X%. You have to have some prior. And, you know, kind of the biggest beef that, if a statistician had any beef with Bayesian ways of thinking and making conclusions, is that where do you come up with these priors? In some areas of statistics, they're kind of made up. So if you have a hypothesis, for example, that this drug will work, which is, you know, sort of how this comes to play. Well, what's your initial probability? Where do you start with? So sometimes it's easy, sometimes it's very hard. But if I understood your question correctly,
yes, that's the question.
Yeah, it always starts, what is your prior belief? And that is sometimes very subjective. I think the answer to that problem is, well, no matter what test you use in statistics, you always have some prior. So for those who follow statistics, if you're doing a hypothesis test, what's your prior with the hypothesis test? The prior is sort of the default position, as in, you know, when you're testing a drug, the prior is going to be, this drug doesn't work until we prove it does. Or if you're doing a poll, whatever the prior poll was from 10 years ago, you always have a prior. You have to, otherwise you have nowhere to start.
How would that, just out of curiosity, how would that relate to issues of faith?
Yeah, great question. I actually, boy, that's a real hotbed topic, and I'll try to broach it very delicately. I think that, you know, I'm actually not going to make any grand pronouncements. I can only speak for myself, which is that I'm somebody who doesn't like to take things on faith. I'm someone who likes to question everything, and from a place of integrity. And for me, I've always been a truth seeker. And what that's led to for me is that, you know, your teachers tell you this and your rabbis tell you that, and, you know, and then the atheists say this and that. And depending on how you're raised, you'll have certain priors. Either this God thing is baloney, or, you know, this tenet of my religion, whatever it is gospel. And I think that for me, you know, the unexamined life is not worth living. I try to really examine issues of faith from that lens of, well, what's the evidence? And by evidence, I don't necessarily mean what's the objective evidence. It's more, what has my experience led me to believe? And try to be really as objective as possible as I can. Not like, oh, I want to believe there's life after death because my life is meaningless and I need this as an emotional comfort. For me, it's really a matter of, well, you know, what is the, you know, is there evidence for life after death? Let's read the studies by Stevenson on near-death experiences. Let's explore the question of consciousness. And these questions sort of led me to really come to conclusions that I'm still, of course, refining, but conclusions about spirituality that led me to think that there's so much more to life than just ashes to ashes, dust to dust. And that's my own conclusion in a very Bayesian way. And this may sound a little weird to some people, but I actually credit probability more than anything else. Probability is what led me to a deep sense of spirituality. It's what sort of woke me up to that, because there were just too many unexplained things in my life in a very personal way. Not that nothing I could prove to anybody else, but in my personal life, I just had too many instances where it was so clear that I was being led, so clear there was a divine guidance, that I just realized that there's so much more. And so that's a very long answer to your question. And it's a deeply personal one too, but I think it's beautiful to question anything that you're told by anybody and anything using your own seichel. Was that a mic drop? I don't know. Any other questions?
I just comment.
Yeah, please.
I very much appreciated the part at the end where you were talking, where you kind of sort of, and what you just sort of said to sort of, add on to it, using mathematical thinking and probability to refine your, sort of belief system or refine your perception of reality. It reminds me a lot, from in a philosophical sense of John Stuart Mill, and his sort of premise that you should always argue based on what you believe to be correct, but with the presupposition that you might be wrong, and like looking for evidence to refute your own beliefs in order to strengthen them or alter them if they're false. It sounds. I like having a mathematical sort of companion to that.
Thanks for sharing, Russ. It's beautiful.
Yeah.
Can you go back to the original problem with the genders of the babies?
Sure can. Sure. Let's see. I'll pull it up here. Yeah, that one is. I always introduce Bayes' theorem in all my classes with this problem because it's just so. People just can't believe how can that be 1/3. But here you go.
So I guess okay. I have 2 children. I just don't understand what the difference is between boy plus girl or girl plus boy.
Sure. In the end, it's the same outcome because you have one boy and one girl. But let's do it like this. Imagine, I'll do it with numbers instead of probabilities. Imagine you have 4 children. One case is going to be a boy, then a boy. One case, on average, is going to be a boy, then a girl. One case is going to be a girl, then a boy. And one case is going to be a girl, then a girl. Yes, in essence, these two have the same outcome in the sense that you have now one child of each gender. But we can consider them different in that they have, they're different ways to get to that. So they happen, it's not like, oh, boy is 1/3 of the time, this is 1/3, this is 1/3. It's actually, this is 1/4, this is 1/4, 1/4, and 1/4. So when we say, given that at least one is a girl, I have eliminated this as a possibility, and I'm left with 3 equally likely outcomes, of which one is a boy, then a girl, one is a girl, then a boy, both of which have the same 1 boy, 1 girl end result, and one is 2 girls. Therefore, the probability you have both girls is this one out of the 3 possibilities they have kept in my denominator. Does that help explain?
Kind of. I guess just with the wording of the question, I don't know why it matters which came first, a girl or a boy.
Yeah, it only matters in that we have to count them as separate because the probabilities would not be the same otherwise. And I'll share with you what I mean. If I just said boy, boy, and a girl and a boy in any order, and a girl and a girl, what would be the likelihood of getting a boy, boy? You would think, oh, it's a 1/3, but it's not. It's not a 1/3.
Right.
This is actually a 1/4. This is a 1/2, and this is a 1/4 again. Okay. So I separate them out just to kind of illustrate that this happens 2 out of 4 times.
Gotcha. Okay.
Great question. Thank you.
Thank you.
Someone asked what happens the days of the week, and just, I wonder if that's where I got cut out, but the days of the week was not meant to be the tricky problem. This was indeed, given that it's not a weekend, it's just 1 out of 5. This was 1 out of 5. That one was meant to be more or less straightforward. I could talk about this all night. I won't be insulted though if you want to go, but otherwise I'll just sit here and have to look pretty.
Thank you. Thank you very much.
A pleasure, really a pleasure. All right, so maybe I will close out just so it doesn't get awkward. Again, have a wonderful night, everyone. Thank you again.
Is there a book that has all of these?
So many. I guess I want to know specifically what you're interested in. Are you interested in Bayes' theorem in specific, or more like sort of counterintuitive mathematical ways of thinking? If so, yes. I'll type it in here. A really wonderful book is called The Drunkard's Walk. Drunkard's Walk by Mladenau. Someone actually posted earlier, I'm not sure if it was private or not, but there's a very popular book now by Kahneman called Thinking Fast and Slow. Someone mentioned that one, which is, he's a very famous researcher on behavioral economics by Kahneman. And that also discusses this. And there are a lot of them, but those are 2 of my favorites.
Oh, thank you. Thank you.
You're welcome. And please send my regards to Shira.
I will. Thank you so much. I will.
Of course. Wonderful to see you.